So before we do dilations, we're doing this last translations problem. And the reason I want to go over this problem is because you're going to see something similar on your quiz next class. On your quiz next class. Yes, you heard me. Now, it says, create an expression in function notation that has a translation left 3 units and up 2 units. And then it's asking for you to write this as an expression. Now, who knows what's the difference between an equation and an expression? Yes, Eli. Exactly. An equation has an equal sign and an expression has no equal sign. And yet, it's still asking for this in function notation. There's only one way to write an expression in function notation, and I'm going to show you how to do it. You know, on our warm-up, how each one of our functions had to have a defining characteristic that shaped the graph. Like the first one was an x squared. The second one was absolute value of x. And the third one was square root of x. Instead of writing those symbols, x squared, an absolute value, square root, you're just going to replace it with a function inside of the expression. I know this is confusing, bear with me. Now, this function is translating left 3. Is that H or K? That's H. And if I'm going left, what does that mean? Good, plus H. And if I'm going up 2, is that H or K? And if it's up, which way is that? Plus. So I know in my expression, I'm going to have a plus 3 and a plus 2. Now give me a letter. It could be any function. Give me a letter. Q. Okay. So we're going to define this function as Q. Now, with the x inside of the function, what do I write? Plus 3. So inside of our parentheses, inside of the function, there's going to be an x plus 3. So right now what I have is Q parenthesis x plus 3 end parenthesis. Yes, Liz?
To write it inside of the expression, would you write it as Q of x plus 3?
Yes. The 3 is still inside of the parentheses with the x. But you're right. Yes. Then, where do you think I'm going to put the plus 2? On the outside of the function, at the very end. Guess what I'm done? That is an expression in function notation. Basically, this expression could be represented as any of the different graphs we went over last class, as any of the different functions. All that this expression tells us is the movement. That's the purpose of this expression. It tells us where the heck we're moving on the graph. So now, part B asks us to write the expression as an absolute value function. So now we're taking those movements and we're putting it into an actual function. So give me a letter. W. So this we're going to define as W of x equals, because this is now an actual absolute value function, it's going to have an equal sign. W of x equals. Now this is absolute value. So does anyone want to take a guess? Go ahead, Eli. Perfect. That's exactly it. So notice, I'm just going to show you, I could have written my expression with any of our functions that we've learned. So I'll do See, I keep asking you for letters because for some reason I can't think of any. L of x. And I'm going to now write this as, I don't know, a cubic. So this is going to be L of x equals x plus 3 in parentheses cubed plus 2. I'm going to write m of x as a cube root. So I'll have the cube root of x plus 3. And then after the cube root, a plus 2. What I'm trying to get at is all the expression told us was the movement. It can be applied to any function. These are examples. L of x and m of x are examples. All right. Does that make sense? And I'm just trying to hit this so hard because they're going to ask for this multiple times either on your quiz or test. So I want to make sure that you get this. We'll do it again today. So you have another opportunity to ask questions. Not that it seems like you want to, but okay. So now on to dilations. Does anyone remember in geometry, when you were dilating shapes, what the heck were you doing to those shapes? Yes, you were taking a shape, say a triangle, and you were making it smaller or making it bigger. We're doing the exact same thing today, but to lines on graphs. Now, just like last class, translations had specific letters in our transformation function, h and k. Those are translations. In our transformation function, dilations has specific letters, a and b. Now, just like translations had a horizontal translation and a vertical translation. By the way, which one of those letters, H and K, H or K, is the horizontal movement? Good. So I'm just labeling H as our horizontal. And then, so which one, therefore, is our vertical translation? K. And actually, everything, there's a misprint on this paper. You should change the absolute value symbols to parentheses, so that it encompasses all functions, not just absolute value. But inside of our functions parentheses will always be our horizontal movements, our horizontal transformations. And outside of the parentheses are our vertical transformations. So, explaining that to you, which letter, A or B, do you think is vertical? Yeah, I literally just labeled A as our vertical dilation. Now, does anyone know, I know this is reaching all the way back to Algebra 1, but does anyone remember a vertical dilation has two things that it can do? What are the vocabulary words for those two things? One starts with an S and one starts with a C. Yes, Mateo? Yes! How'd you get that? Did you just remember? Oh my, okay, well, at least you're honest. Yes, good. It's a stretch or compress. Stretch or compress. Now, hopefully in your heads, you're wondering, okay, how do I know which is which? If your A value is bigger than 1, so I'm making it bigger than 1. Everybody, look at my hands real quick. So in Algebra 1, they did this with balloons. Don't have a balloon, I'm so sorry. But on the vertical, which do you think that's the y-axis or x-axis? Yeah, the y-axis is our vertical. If I'm taking my y-axis and stretching it, oh shoot, I screwed up. I meant to say, and I'm making it bigger than 1, do you think that's a stretch or compression? It's a stretch.
Oh, you mean the B value, not the A value?
No, I mean the A. A is always the vertical on the y-axis, and B is the horizontal on the x-axis. So if I'm stretching it, it means I have an A value bigger than 1. And what does the graph look like if I'm stretching it? Skinnier or wider? If I'm vertically stretching it. Skinnier. Good. So here, I know that I have a vertical stretch because my A value is bigger than 1. And I'm going to write a little note to myself that the graph looks skinny when I'm vertically stretching it. So, if when A is bigger than 1, it's a stretch, what do you think makes the graph vertically compressed? Ah, yes. If A is less than 1. So, if I'm compressing this time, I'm compressing on the vertical. I'm compressing my y-axis. Is my graph looking skinnier or wider? Wider. Now, can anyone take a guess, a stab, at why the heck did I put absolute value symbols around my A's? What do you think that gets rid of? Absolute value. What does absolute value get rid of? If I had the absolute value of 4, negative 4, what would you tell me? It's a positive 4. What did it get rid of? The negative. I wanted to get rid of the negative in this situation because a negative in front of A has nothing to do with the stretch or compress. A negative in front of A actually does a reflection, which we're not learning about today. We're learning about next class. Okay? So I want to make sure that you guys know negatives have nothing to do with the stretch or compress. If the number itself is bigger than 1, it's a stretch. If the number itself is less than 1, meaning 1/2, 1/3, 1/4, 2/3, it's a compression. Okay. Also, well, let's look at some examples of A first before I talk about B. So let's look at this graph right here for our vertical dilations. First of all, in this example, our first graph, what is this parent function? Yes. It has that U shape, right? That parabola. And what's the equation for my parent function of a quadratic? X squared. Good. Now what I want you to do is on this graph, I want you to draw the parent function. I want you to go ahead and draw the parent function on this graph. So, I do place a point on 0, 0 for my parent function, but then what else do I graph? Yes, up 1 over 1, up 1 to the right 1. And also the mirror image of that, up one to the left one. And when I was doing this in my notes, even went a step further and looked at my parent function. From that point. I always start on the origin for all of my points. I go over 2, up 4. Over 2, up 4. But however you get to it, I don't care, as long as you know those are also perfect points. So here, I have the points 2, 4, and negative 2, 4 as well. This is my parent function. Woo! Oh my gosh. Come on, Miss Sunderland. Well, now it looks like absolute value. We're going to go with it. We're going to go with it. All right. The reason, I'll just say, the reason I wanted you to draw the parent function, do you notice that the new function, the red line, g of x, they're calling it, is it the same width? It's skinnier. It's skinnier. And what did we say having a skinnier graph means? A is more than 1. A is more than 1. If it's a stretch, if it's skinnier, A is bigger than 1. Okay? So this purple line I drew is my original, and the red line is my g of x. Because it's narrower, it means I have an A value. Now the trick is finding the A. Do you notice on the parent function how we went up 1 over 1 to get to our next perfect point? Yes. On this new graph, we went up 1, 2, 3 over 1. Exactly. So anyone else want to take a guess, a stab, at what maybe A could be on this graph? We know A has to be bigger than 1 because it's a stretch. From one perfect point to the next, we're going up 3 over 1. What do you think the A value is? 3, exactly. And in my function, where does the A value always go? In the very front. So the first thing I'm going to write to define this new function, g of x, is 3. Now, do you just think this is x squared and we're done with 3x squared? No. Where else has it moved? Up 1, 2. And is that an h or a k? That's a k. And if we're going up 2, is that plus k or minus k? So does anyone want to guess at how we're going to finish writing this equation? Richard. I'm sorry, Eli. Exactly. It's a quadratic, meaning it has an x squared. And after the x squared, I put a plus 2. So in total, I have 3x squared plus 2. So this graph has done 2 transformations. It's been vertically stretched by 3. Vertically stretched by 3. And it's been also what? What else has it been? Yes. Translated up 2. These are the transformations. Yes. Thank you for asking, Miss Lovenstein. These are the exact words I want to see. If you write shift instead of translate, it would be not marked correct. If you forget the word vertically, you won't get full credit. You need good vocabulary when dealing with transformations. Okay, just like we did on the previous page, page 4, this number 1, I want you guys to try this example, writing another expression in function notation. So you guys try this example, create an expression in function notation that has a vertical compression by a half, a translation right 2 units, and up 5 units. Go ahead and try it. And the expression, what number was written first? 1/2. Then what came after the 1/2, Elvis? What did you write right after the 1/2 in part A? Perfect. Then we write the function notation. Then what did we write, Isabella? Yes, x minus 2. Because we're going right 2 units. That's where our minus 2 comes from. And then what did we write, Kennedy? Plus 5. Perfect. That is our expression in function notation. Now, what did you write first in part B after the g of x equals, Mateo? Yep, 1/2 again. Now here comes the tricky part. What did you write next, Ava? Perfect. We're replacing the function notation of g parenthesis with the actual notation of absolute value. And then what did we write, 8 and f? Exactly. And now we have written an equation, an actual absolute value function. I literally pulled this problem from the quiz. Change the numbers. I'm not that nice to you. But same verbiage, same problem, different numbers. And probably changed the right and up. Not too sure. Not 100%. But this is from your quiz. So every time I tell you that, and I do tend to say that a lot, you should be putting stars or some indicator that this is important. Any questions on this problem? Okay. So now, I'm going to do, well, we'll do these together just to save us some time. Normally, I'd have you do these on your own, but we're going to do them together, and I'm going to pull sticks. So be paying attention. I'll do A first. Part A is asking you to write or name the transformations here, meaning we're using our great vocab words. So on part A, notice how there's a 2 in front of the absolute value symbols. What letter is 2? A, B, H, or K? A. And A being 2 means that A is bigger than 1. So what type of transformation do we have here? Yes, it's a stretch. What do I need to say in front of stretch? Vertically stretch. You can put a V. Vertically stretched by how much? By 2. You have to say by how much? By the scale factor, as it was called in geometry. All right. So on part B, what would you call, or what is the first word you would say for that transformation, Kaylee? Just the first word. Vertically. What's the second word for part B that we have, and it says 3x cubed? So is that a, hold on, Liz, if it's a 3, is that a stretch or compress?
Stretch.
Yes, so we say vertically stretched. And then what do we say lastly? Jay's not in this class. Whoops. Vea. Yes, by 3. Okay, on part C, 1/2 the square root of x. Eli, what's our first word? For part C, yes. If you want to, Eli, go ahead. Vertically compressed. And how did you know it was compressed? Because a is less than 1. It's a fraction. And it's by 1/2. Part D, what's our first word? Aiden D. Yes. I hope you noticed ooh, you even gave me the next word. Yes, compressed. You want to just finish it up, Aiden? Yes. Perfect. On your quizzes and tests, this is how your vocabulary should look. If you're not writing these full statements for the transformations, you will not get full credit. I will accept V because I'm writing V. Yes. I am lazy, and I'm sure you are lazy. You'll notice, as you go higher up in math, mathematicians are lazy. They are the laziest people ever. So that's why we have all of these abbreviations for everything. So are chemists? Okay. We're all lazy. We're just super lazy. Yeah. Okay. So now, before we're done with notes, and before I give you your homework, which is actually a quizzes today, we're going to look at B. Now, we're not going to go too in-depth with B. We're not going to do too much with B. But we do need to take a look at it. So back up here at the top of page 5. We just went over our vertical dilation. What do you think B describes? Oh, yes, it's our horizontal. Now remember, I told you, everything inside the parentheses is always what? And also, starts with a B.
Backwards.
Yes, backwards. Backwards from what you think. So knowing that B also is going to behave backwards from what you think, if B is bigger than 1, do you think that's a stretch or compression? It's a compression because it's backwards from what you would think. And if B is less than 1, therefore, what is it? It's a stretch. I'm still using absolute value symbols around my B because negative has nothing to do with the compression or stretch. A negative in front of B actually reflects it, which we'll learn next class. Now, on the horizontal this time, which is which axis? Take a look at me. Look at me. On the x-axis, I'm horizontally stretching and compressing. So if I'm taking my horizontal axis and I'm compressing, did my graph just get skinnier or wider? If I'm compressing, skinnier. Remember, it's backwards from what you would think. So horizontally compressing actually makes the graph skinnier. And if I'm horizontally stretching, what's happening? It's getting wider. Good. Okay. So now, let's look at a graph. Let's look at this graph. And I'm just really quickly here going to draw the parent function for this. This is, what type of parent function is this, by the way? It's a cubic. It's a cubic. For this example, under B, horizontal dilations, this graph depicts a cubic. And what does the function look like? What is the equation for a cubic? Parent function. X cubed. Good. So I'm just really quickly going to draw my parent function centered on 0, 0. I have a perfect point up 1 over 1 from my origin. I also have another perfect point down 1 to the left 1. So, does my new graph depict a horizontal stretch or a horizontal compression? Does it look, let me ask this, does it look wider or skinnier? Wider. And wider, is that a horizontal stretch or compression? If I go wider, I'm stretching. Now, if I'm looking at this graph from the center of my new graph that's on 3, 0, to get to my next perfect point from the center, how much did I go? Up 1 over 2. B is a half. B is a half. So, in my equation, this is a cubic. B goes right in front of the X. So I'm going to have a 1/2 in front of my X, and it's all going to be cubed. Yes, where'd you get the -3 from, Eli? Why did we say -3? We went also to the right 3. That's my H value. So inside of my equation, I also need to put a -3. So in total, I have parenthesis 1/2, another parenthesis, X minus 3, n parenthesis cubed. Any questions here? We will not make you find B on a graph like this on your quiz or test. All right? I just wanted to show it to you, show you what B is going to look like on a graph. You are going to have to look at an equation, see that 1/2 is in front, right in front of the X, so therefore it's a B. You will need to know how to do that. We'll tell you. Okay, so go ahead and do this next example. This is more going to be like what you'll see on your quiz. Do the next example for the expression 1/3 f 2 x minus 3 plus 4, write this as a quadratic function and then state the transformations. So there's one thing I need to tell you before you do this. Remember how I said b is backwards? When we are stating the vocabulary, when we're stating the transformations, because b is backwards, and in our previous example, b was 1/2, we do not say horizontal stretch by 1/2. What do you think we say by? How did you know that?
Well, I had to think about it because you said backwards, so I was like, well, it can't be stretched because it wasn't stretched, so the other thing has to flip.
Exactly. We say by 2. We flip the fraction. Anytime we're dealing with a horizontal stretch of compression and we're stating the transformation, you say it's by the reciprocal. You flip it and we say by 2. Whenever we're having a horizontal dilation, you always flip the fraction. What?